Okay, I think we are going to go ahead and get started. Before I introduce today's speaker, just a word about our next seminar, which will be 2 weeks from today on April 25th. It will be the last seminar for this semester before the fall. And that speaker will be Professor Yang Ki from Biomedical Engineering. So it's a pleasure to have with us today Professor Marta Hatzell from Mechanical Engineering. Marta got her bachelor's, master's, 2 masters, and PhD in environmental engineering, all at Penn State, where she was an NSF and PEO graduate fellow, and then did a postdoc at the University of Illinois, Urbana-Champaign, in material science and engineering, before coming to Georgia Tech in 2015. In looking over her bio, she's won a ton of awards, particularly recently, and I'll mention just a couple of them: an NSF Career Award, Moore Inventors Fellowship, Office of Naval Research Young Investigator Award, Sloan Foundation Fellowship in Chemistry, and hot off the press, the Georgia Tech Outstanding Achievement in Early Career Research. And with that, I will turn it over to you.
Happy to also just take questions throughout. This is obviously very informal, and so if something strikes you and you have a question, as with all classes, feel free to interrupt me. I'm happy to talk just broadly about this topic, which is basically about the role. How can you use electrons and photons to basically do chemical manufacturing and environmental remediation? And so this is broadly important as we're seeing the Inflation Reduction Act and all of these other bipartisan infrastructure laws and everything like that. There's a growing need to figure out how can you decarbonize, and electrochemistry and electrocatalysis is one option for especially chemical manufacturing. And so, in general, my groups at Georgia Tech is called the Circular Electrochemistry Lab because, in general, we're looking at a lot of energy and environmental applications where we're trying to, create circularity in that process. And so, here's one of those examples: is nitrogen. And so, just because this is my research group here, so we have many different researchers working with us, but I want to acknowledge them. The people today I'll be presenting work completed by Jung-Hoon Lim, who is listed here. He's actually graduated and now he's a postdoc at Lawrence Berkeley National Lab. And then also Carol Liu, which is right down here, and she graduated a few years ago in environmental engineering and now is at Intel, actually. And so again, many collaborators as well, some at Georgia Tech and some elsewhere. So what motivates my group is that there is this growing need to get to net zero and decarbonize all industrial sector, industrial, transportation, municipal, buildings, all of it. So down here is electricity and heat, industry, transport, buildings, and other. And so here's 2020, around where we are today, and here's 2050, where we want to get to, which is basically net zero carbon emissions. And lots of companies and governments and consultants have looked at what the pathway should look like to get to net zero carbon emissions by 2050. And it's not going to be done on one day. It's going to be through many different changes being made to these various energy consuming and carbon emissions heavy industries. And so so this is generally why we do what we do in my group. And how we think we fit this goal of net zero is through electrifying industrial catalysis and separations processes broadly. So my group works in these things. We want to separate things, or we want to convert them from one molecule to another. And so that's catalysis and then separations. And right now, both catalysis and separation is in every industrial process, from pharmaceutical manufacturing to chemical manufacturing for fertilizers. And there's various forms of catalysis and there's various forms of separations, but the majority of them today rely on thermal energy, high process heat, which then requires, or is today reliant on fossil-based fuels. And so if you can electrify, you even if you're electrifying to make process heat, that's a huge way to decarbonize these industries. And so what we look at in my group is, from a separations perspective, membranes for separations such as desalination, but also for other separations as well. We're also looking at electrochemical separations for mineral recovery, specifically for lithium-ion batteries recycling. And then in the catalysis space, we're looking at how can you use electrocatalysis, which is basically electron-driven catalysis, or photocatalysis, which is solar-driven catalysis, or also looking at whole systems like electrolysis cells. And so these are generally the area of separations and catalysis that my group's interested in, but they all fall into this orange curve here of how, if we can do these things, then we can help decarbonize this orange, which is the industrial sector. And so with that, I'll switch focuses and now talk a little bit about why nitrogen. So you hear a lot about carbon emissions, and you've probably been very aware of things like your carbon footprint, and understanding that we need to mitigate combustion-based processes, or at least capture CO2. But what you're probably less aware of is the environmental implications of the nitrogen cycle. And so this is a paper from actually 2008 by James Galloway. He's a really famous geochemist from University of Virginia. And they basically have come up with a lot of papers basically trying to model the imbalance in the nitrogen cycle. It's really hard to make these measurements. They take years of collecting Earth-scale data sets to make these projections. But what his group highlighted back in 2008, which seems like a long time ago, was that there's a lot to see here, but you have land, you have ocean, and you have the atmosphere. And they're able to quantify what are the predominant forms of nitrogen in the atmosphere, land, and ocean. And they were able to look at how the fluxes are varying as a result of anthropogenic activities. And so what you need to see here is basically the orange basically arrows are anthropogenic sources where we're inputting nitrogen into the atmosphere that wouldn't be there without humans, right? Whereas the blue curves are what naturally the transformations of nitrogen in the land, atmosphere, and ocean, which we know exists. Just like there's carbon fluxes across our globe, there's also nitrogen fluxes, which we expect, biological transformations in soil, and so forth. And so when you look at this orange region, which is causing the imbalance, it really is tied to two different things: fossil fuel burning and fertilizer application. And the interesting thing is that this is in 2008 again, and the data was collected in the 1990s. And so, in fact, fossil fuel burning and NOx emissions associated with fossil fuel burning, we've made actually significant progress in decreasing this anthropogenic source. But over that same span of time where we've been increasing the efficiency of our catalytic converters and capping emissions from power plants and creating policy to mitigate this flux, we've not been doing the same with fertilizer application. And in fact, we've been accelerating or increasing the input of fertilizers into our nitrogen cycle. And so this is just really to show you that. And the interesting thing is, if you look at this, again, it's maybe hard to see, but there's the biological carbon cycle, the nitrogen cycle, and our phosphorus cycle. So these geochemical cycles are interrelated. So as we shift, even if we start to balance our carbon cycle, an imbalance in the nitrogen cycle will also imbalance the carbon cycle. So we need to care about all of these geochemical cycles. And so that moves us to, so nitrogen is really important. Fertilizer is primarily made up of nitrogen-based species like ammonia and nitric acid. And so what we can see about ammonia is, if we look at all the chemicals that are produced today, ammonia has the largest greenhouse gas emissions associated with any chemical. And this is predominantly just because of the sheer mass of that chemical. So here you can see it's about over 150,000 tons per year. So we produce a lot of ammonia. So we have a lot of greenhouse CO2 emissions associated with the production of ammonia, and then greenhouse in metric tons of CO2. Close behind it is ethylene, and so ethylene is also used in lots of different things that we use on a daily basis. And so ammonia and ethylene, if we look at what we want to decarbonize first in terms of chemical manufacturing, it's probably these two commodity chemicals because they're really have a large energy and CO2 footprint. And the interesting thing about ammonia, we need it for food, so we can't decrease production of it anytime soon. Ethylene, we need it for, again, a lot of different things. So I don't see us just decreasing consumption. And here's the projected, the projected CO2 emissions to 2050. For ammonia alone, it could get up to 1,000 metric tons per year. And here is the 2 degrees. This is the path that we actually need to go with ammonia. And so the interesting thing with ammonia is that we don't need to necessarily get to zero carbon emissions associated with ammonia, but we do need to decrease the carbon emissions associated with ammonia. And so that's what we're trying to design technologies to move this towards this scenario rather than this scenario. So how do you produce ammonia today? Well, essentially, we just use a material that is called a catalyst that can preferentially bind two molecules, nitrogen and hydrogen, and then lower the activation, and then hopefully that material lowers the activation energy associated with performing some sort of catalytic reaction or some sort of chemical reaction. And so this is essentially an example of like what a catalyst surface might look like. It's just a surface. And here's our reactants, nitrogen and hydrogen. And then we get it to the surface, we adsorb nitrogen, we hopefully break the triple bond, and then we get this adsorbed nitrogen species, and then we can hydrogenate that to make ammonia. And so that's ideally what we want, and that's what happens today with the Haber-Bosch process. And so the Haber-Bosch process is very efficient. It's upwards of 60% energy efficient, so it's very, from a chemical engineering perspective, very advanced. But to do this, you need to have the right material to form all of these intermediate processes. And then you also need the right thermodynamic operating conditions. And so essentially you need a high temperature to help break the bonds, the triple bond, because it's one of the largest or strongest bonds in nature. But when you go to high temperatures, you switch the equilibrium, and so this reaction doesn't want to take place. So then you also need to increase the pressure. So you need to basically calibrate your system to a temperature and pressure so that nitrogen actually breaks and that it forms ammonia and that ammonia oxidation doesn't take place. And so this has been, again, optimized. It works. But elevated temperatures and pressures, again, are sometimes not ideal because they only operate at large scales. And so oftentimes, when you look at these Haber-Bosch plants, if you look at scaling chemical manufacturing, the only place that this makes sense is to do really, really large systems. And so today, there's about 100 Haber-Bosch plants across the world, but they're massive. And they cost billions of dollars to build. And so this is how it happens today. And interestingly, the largest carbon footprint for this process, you can see no carbon in this here. So if I'm trying to decarbonize this process, it's not necessary that this process is actually bad. Unlike combustion in your engine where you actually emit CO2, there's no CO2 here. But the largest carbon footprint is due to the production of this molecule, hydrogen. So today, we can decarbonize actually the Haber-Bosch process quite easily, and this is being done in places like Australia, where you're basically, instead of using steam methane reforming, you basically take water electrolysis, and you get that hydrogen from water instead of getting that hydrogen from a fossil fuel. And that way, it basically is, you have renewable energy, water electrolysis, and this same Haber process, so that stays the same. And so that is definitely our near-term solution for decarbonizing ammonia production. But again, you're not able to get over that issue of scaling the technology. You're still reliant on this process, which is high temperatures and high pressures. And so you're still looking at billions, multi-billion-dollar technology or systems to basically manufacture ammonia. So this will definitely be a route that we see emerging. But then there's this other question is if we can think about alternative approaches to manufacturing ammonia that could be important for reaching places in the world that can't access ammonia, or for decreasing the carbon footprint associated with all the transport of ammonia that's necessary. And so we're looking at these alternative pathways to meet that need. And so what I call this is decarbonized and partially electrified is going to be what we're going to come first. And then decarbonized and fully electrified is another pathway that we're looking at. And so again, just another reason why why do we need to have scalable technologies? So all the black dots are where we have ammonia production plants. So we have a lot of ammonia production in North America. We have a lot of ammonia production in Russia and Europe. But South America only has a few, the whole continent only has a few Haber-Bosch plants. The whole continent of Africa only has about 1 or 2 plants, and so there is significant challenges. Interestingly, you probably remember the Beirut explosion that took place a couple years ago, and that was an example of someone trying to ship these highly concentrated fertilizers from Europe all the way to Mozambique. It never got to Mozambique. It stopped, and due to political reasons, it just got stored in a non-safe way. But the question should be asked, why were you shipping it 3,000 miles in the first place? But that's because there's no Haber-Bosch plants in this region. But the second thing is that if you look at this heat map, the heat map is the cost-adjusted distance for that fertilizer. And so again, you can see the cost of getting a fertilizer to different regions in sub-Saharan Africa is significantly higher than the cost that we pay in the United States. And if you weren't following this last year, the price of fertilizers quadrupled last year for us in the States, to the point where some farmers in the United States were deciding not to apply fertilizer because it was too expensive for us. So if it was too expensive for us and we have the resources right there, imagine if you're in someplace in Peru or some other location where shipping was even compounded that probably by 10, 20, 100 times the cost. And so there's certainly a need to come up with decarbonized, electrified, and what we're calling potentially decentralized production processes to increase equity. So if we want to come to these other technologies, how can we do that? From a catalytic perspective, the first thing we're going to look at is, can we come up with new technologies, new materials, and understand new reaction mechanisms? So the last mechanism, which may not be burned in your brain like it is in mine, is that process where nitrogen first has to adsorb to the surface and breaks. And that breaking that triple bond is really challenging. So there's alternative mechanisms. Maybe instead of breaking that triple bond, maybe you just adsorb, and so this is the process. Maybe instead you are able to adsorb that nitrogen intact, so the triple bond's still there. And then you can have a catalyst that allows for the hydrogenation of that adsorbed nitrogen. So, and as we add other atoms to molecules, we can basically slowly weaken that triple bond. And so we can slowly break the triple bond by hydrogenating it, and then that lowers the energy required for that catalyst to break the triple bond. And so a lot of people think that this is the potential catalytic pathway that we would use if we started to lower the temperature, lower the pressure, and move towards these green technologies. And so this is the associative mechanism. But there's also alternative feedstocks that we can look toward to get fertilizer. So fertilizer is really anything where the nitrogen bond is broken, because nitrogen is everywhere, right, in the atmosphere. But for the plant to be able to utilize it, it has to be broken down, and it can't be in that N2 form. And so it could be nitrite, nitrate. It could be maybe not, we don't want hydrazine, but it technically could be. And so we can look towards the biological nitrogen cycle, and we can see there's actually lots of different reactions that we can use, and lots of different products that could be valuable for us. And one that stands out is actually using nitrate, because nitrate is a widely used, well, not used, it's widely found in a lot of our groundwater today, and it's actually bad for our public health. And so we actually have to treat all of nitrate, or we want to treat nitrate because it's bad for the environment, it's bad for our public health. And so perhaps there's alternative pathways, like we can use nitrate to recover that, or we could go and convert that to ammonia. And so this is just a perspective on, there's lots that can be done, and lots of different feedstocks that we can use other than nitrogen, and we also have to look at different reaction mechanisms as well. And so what my group has been working on is, and specifically as it relates to catalysis, is these two different processes, electrocatalysis and photocatalysis. Electrocatalysis is taking that catalyst that maybe would traditionally be in a packed bed reactor in a thermocatalytic processes, and then we basically bind it to a conductive surface, and then we can supply electrons to that material. And then those, based off the electronic structure of that material hopefully binds the reactant, and then the electron or hole combines with our reactant to get our product. With photocatalysis, it's slightly different. We usually use a semiconductor material that, when illuminated with sunlight, photogenerates electrons and holes. And so in a way, photocatalysis is still an electron or hole-driven process on a solid surface. But the difference is that a photon is the reason why you're generating those electrons and holes. Whereas here, we're directly generating electrons using a power supply. So I'm going to try to walk you through two of these projects and talk you through what we've been working on. And so again, this is the nitrogen cycle. A lot of people have looked at how you can convert, and our goal is to convert this nitrate to ammonia. A lot of individuals have looked at this for a very long time. And it was interesting in the early 2000s, and a group out of Mark Coper basically said, this is a 10 electron transfer process, so that's a lot of electrons that you need to convert nitrate to nitrogen gas, because for the most part, people were looking at this for remediation, as I mentioned, water treatment. And so it was deemed really not going to be possible unless you could get 100% selectivity. And what selectivity means is I want to go from nitrate all the way to nitrogen, and I don't want, but I have to go through all of these intermediates, and so they all have to go in a series. And so sometimes a reaction can stop at nitrate, and it may not go all the way to nitrogen. So that would decrease your selectivity. And so it was a lot of research was done, but it was deemed probably not likely because you need these really ridiculous performance metrics. And then the other alternative that more recently people have been looking at, Mark Roper's group in addition, is how do you valorize this? And so instead of going from nitrate to nitrogen, can we go from nitrate to ammonia? And because we know ammonia could be very valuable. It's been, what people have found is that there is renewed interest in it, and it seems like the catalysis is reasonable. And so how does this happen? Again, maybe this is too many reaction mechanisms for you, but the idea is that you have two steps. First, you need to get nitrate to adsorb to the surface. And then the second thing you need to do is you need to get nitrite to not poison the surface. Nitrite likes to actually just stay on the surface and poison the catalyst. So you need to be able to find a material that can adsorb nitrate and desorb nitrite. And then you need to have catalysts that can help you either couple your NO to get to nitrogen, or not allow NO to couple to each other so you can get to ammonia. And so there's lots of different materials aspects associated with designing these catalysts, because there's lots of different intermediates, and different reaction pathways you could follow. But generally, researchers have found, and this is Marta Figueroa, she's in the Netherlands, and she's done quite a bit of work on this. And really, a lot of her PhD work really pointed to that you need, again, palladium and platinum weakly bind nitrates, so they're not ideal for nitrate reduction, but palladium and platinum are very active for this second step, nitrite reduction. And so basically, what people have found is that you kind of need two different materials, one that reduces nitrate and one that reduces nitrite. Nitrite palladium seems to work for that. And then for nitrate, you can be looking at other materials like copper. And so copper has been the most widely used for nitrate reduction. And so what we've been looking at is how can you look at using, how can you design these catalysts so that they can do these two steps in a way that can improve the rate of production. And what is the role of surface structures plays. So when you buy materials from a distributor like Sigma Aldrich, you'll get most of the material will be in really the most thermodynamically stable form, which is usually polycrystalline. Those will have different surface facets, and that all affects the binding of our reactants and intermediates. And then a third question that we've been looking at is, okay, if you need to make biometallics, what is the most efficient way for these biometallics to be oriented so that you get the optimum properties of both the copper and the palladium. And so coatings, alloys, and all of this has been what we've been looking at with a focus on basically evaluating the selectivity and stability. And so this is, again, work that was completed by Jung Hoom. And so what he first did was looking at how do you create these nanocrystals through controlled growth. It's really easy to, well, it's not easy, but a lot of times when looking at facets and looking at fundamentally what's happening at a surface, people like to create films with certain exposed facets. So we can look at what's the effect of a 100 facet or a 111 facet. And then we can ascribe catalytic activity to that film. But a film is not going to be that helpful for us because we need high surface areas. And so moving towards nanocrystals with controlled facets is of importance. But ultimately, we would want to identify what has high activity and then design the catalyst. And so here our goal was to design the catalyst and see if we could look at the catalytic activity and ascribe it to the different facets. And so he created these nanocrystals where we had 100 facets, so these are nanocubes, and then these cubooctahedron, which had both 111 facets and 100 facets, these octahedron, which had the 111, and then also concave nanocrystals that had basically highly faceted nanocrystals. And we benchmarked all of this against palladium polycrystalline catalysts. And so this was the first thing he looked at. Then he looked at, okay, well, once I can look at the activity of these crystals, can I then add palladium and copper, I should say, and looked at how you could manufacture this copper through just coating with copper. And then the third thing we wanted to look at was if maybe coatings are not the most active or most ideal because there's going to be different surfaces that we want. And so we're looking at if we could create ordered and disordered alloys. Again, so one problem with coating metals is that they can migrate through the catalysis, and so this can be a non-stable form of a catalyst, whereas when you move to alloys, the thermodynamics seem to settle out and you can get potentially more stable performance. And so that's what we were looking at, and if you're familiar with nanocrystal growth, it's really hard and it needs a lot of time. And so but it really, all you need is a seed, and then you need to add ligands or surfactants to basically cap off different ends of the metal to allow for the growth of nanocrystal in the desired direction. And so luckily, there's been a lot of work in this area, and these are papers which demonstrated this first growth in these nanocrystals. And so we were able to luckily draw from literature. Despite there being literature, I do commend Jung Hoon on his work because it is even a little bit of contaminants in your cell can completely derail the crystallization process here. And so again, we looked at these for catalysts and we compared this to palladium and on carbon commercial catalyst. And if you're not familiar with electrochemistry, this is an example of a cyclic voltammogram, and generally it tells us a little bit about the activity of our catalyst. So on this y-axis is your current density, on your x-axis is the potential. Ideally, we want to be able to get high current density because that relates to the turnover of the reactant at a low potential because the potential depends on drives our energy up. And so this is basically, and here's these dotted lines, which you may be able to see, are the control experiments which have no nitrate in the cell. And the reason why you have to run those is because you can also evolve hydrogen. And so here we want to selectively reduce nitrate, but we don't want to reduce water to hydrogen. And so these show us how much current is going to a reaction we don't want, which is hydrogen. And so what you can see first off is that there is significant difference in the catalytic activity as you change the nanocrystal size. I will say the surface area is the same in all of these cells. And so the differences in the current is really just due to the different exposed facets of these nanocrystals. And what we see here is that the cubooctahedron and the octahedron had the highest current density, whereas the concave and the nanocube had the lowest current density. And so this is another way that we can look at that, where you can decouple the current that's going to that hydrogen reaction versus the current that is going to nitrate reduction. And the interesting thing that arose here is that this 111 facet really seemed to have a preference for nitrate reduction. Just a reminder, palladium is the metal that doesn't bind nitrate. And so we actually think palladium is not so great with nitrate reduction. And so what we're really trying to do is amplify that. And so what it's saying is that, yes, palladium is not great for nitrate reduction, but if you do want to design your catalyst so that it has some activity, you'll want to look for designing the catalyst with the 111 facet. And so then we also looked at, so this is nitrite reduction. Remember, we have these two different reactions. We need both of them to be accelerated. And so now he's looking at putting nitrite in the reaction. Palladium is good at nitrate reduction. So unsurprisingly, it's pretty excellent, and it doesn't really matter which facet you have. You're getting pretty similar performance. I mean, there is the nanocubes seem to have slightly enhanced performance, and so it seems like the 100 facet is slightly better for the nitrite reduction, but in general, we're not really worried about palladium and this reaction. So, but there is some surface structured effects. We worked with Tom Sneffel. He's an assistant professor at University of Rice, and he's an expert in DFT. And one thing that's really important when doing these controlled studies is we can see our bulk experiments, and that gives us some information about how the reaction is proceeding. But it's also great to augment it with either in operando experimentation to prove that the reaction is moving quickly, or augment it with theory. And his group has actually, they're kind of leading experts in this area of understanding specifically nitrate and nitrite reduction. And so what he did was, and his research group did, was look at the adsorption energies for nitrate and nitrite on these various controlled facets. And really what he was able to show was that nitrate adsorption and dissociation was almost over 10 eV higher for this palladium 100 over palladium 111. And so, it basically, why we were getting better nitrate reduction was really just due to this decreased adsorption energy. And that's what we thought from our experiments, but it was good to confirm through theory that was able to adsorb nitrogen, that decreased the barrier for nitrate to get to the surface. And then he also found that nitrite desorption was almost 0.2 EV more favorable than on palladium 111 when compared to the 100 surface. Again, a potential indicator of why we saw better nitrate reduction. I will note that 0.1 and 0.2 EV are, from a catalysis perspective, are significant in improving the catalytic activity. So by improving something by 0.2 EV, that does help. And so as I mentioned, we then moved on to looking at adding, we know we needed a promoter metal, so we know we can't just get away with palladium, but that gave us some good insights on palladium. So we need to add copper to a catalyst, and the question is, how can you do that? And so we looked at two ways. One, which is an electrochemical manufacturing approach, which is basically to use under deposition potential to basically take copper and deposit it on the surface. This is actually somewhat precise. I mean, there's ALD and all these other techniques which can get you really atomic scale precision. But electrochemical deposition is actually also at that scale where we're getting really almost atomic level deposition of metals. And so it is actually, and it's a scalable manufacturing method as well. And then the second approach that we looked at is by actually just trying to make alloys where the copper was interdispersed in the metallic catalyst. A very simple way to do that. We can do this in the wet lab and do this with traditional manufacturing methods. But a lot of times you get these random ordered catalysts. And the challenge with that is that throughout your catalysis, the atoms are going to be constantly migrating in the metal. And so you may have changes in product selectivity. As we saw, very slight changes in a surface facet changes catalysis. And so if they're not stable, you could also see changes in catalysis. And then the other thing that we looked at was basically creating these alloys that were ordered. And so this is one way that if you create them in a very well-ordered alloy, the atoms are not likely to move, and so you might have more precise catalysis. And so we looked at these different ways of basically making copper palladium nanocrystals. And so this is an example of the manufacturing process in the lab that we use, where we basically can look at doing various basically sweeps through oxidative and reductive potentials, and we can see really clearly both oxidative and reductive peaks, which says that current is being used to either deposit or strip metal from our surfaces. We can basically look at these various potentials. So C1 here is when copper is deposited, and so that's right here. And C2 is the bulk deposition, and then bulk dissolution, and then the under potential desorption. And so what we started out with looking at is just taking those nanocrystals that had that 110 facet and looked at seeing if we could basically deposit these. And so this is some high resolution TEM that we went to actually Oak Ridge to do because, and this is what we were able to show is that you do have palladium in the core, which we expected. The surfaces are, you do seem like they are shifting a little bit, so we're not getting, we want these really flat surfaces for the 100, but it does seem like especially the corners are starting to shift. But we do seem to have the copper at the edges. And so this showed that we were able to basically look at fully covered nanocrystals where we have it fully covered, and then this partially, so we basically stopped during the deposition. And we seem, again, this is what we believe we're seeing. There's still copper all along the edges, but it seems like the corners are rounding out and there's a lot less copper there. We also did ICP-MS to quantify the amount of copper and palladium for these different catalysts. So we looked at these two different catalysts. And the interesting thing that we saw was that the fully covered copper catalyst you basically made all ammonia. So this blue is ammonia, the orange is nitrogen, and the pink is nitrite. And so when you had you had a core of palladium, but then a complete surface coverage of copper, you only made ammonia. Whereas if you had a partially covered copper, just a little bit exposed, if we go back to here, it's still covered in copper, but maybe a less thick layer, we're getting nearly all nitrogen. And so I think this really showed like how quickly or how different your catalyst selectivity can be depending on what surface you have. And then here is, again, this is the palladium. And so it's a really interesting thing that you can see basically having palladium, you get mostly nitrogen, a little bit of copper, and you still get mostly nitrogen, but then covered in copper, and it switches completely from a nitrogen selective process to an ammonia selective process. I'm not showing all of the data, but one thing that we always do is we try to look at the stability over a long period of time. And so this is an example of the partially covered nanocrystals and the stability. Again, the most important thing here is that you see that it's pretty stable. The orange amount, which is nitrogen, is changing, but not substantially over many cycles. Again, we worked with Tom to look at what was happening on these surfaces. And so we looked at the theoretical underpinnings of the adsorption and reaction processes. And the interesting thing that he found was that we really are proposing that there is like some spillover effect where basically you're basically getting, you're binding nitrate and nitrite to the copper and the palladium. But that the NO adsorbed species are actually able to spill over from the palladium to copper, and that this is a really important step in making nitrogen. So you need two NO species to couple to make nitrogen, and so by having that specific interface between the copper and the palladium, you're able to get that selectivity towards nitrogen. And you can use that knowledge to then think about, well, if I don't want that spillover effect to make ammonia, how do I design interfaces that can make ammonia? And so this is just generally some of the reaction steps. So this is how we get to basically nitrogen, and this is how we can get to ammonia. And so the last thing that I'll talk about is that, again, moving from basically, again, we know we need these two materials. How do we configure them? I said that, from these experiments, I'm seeing stable performance. But again, we do need to do some more ex situ characterization, because I'm very certain that at points, eventually the copper would migrate into the bulk, somewhat creating an alloy. And so there is stability, but long-term stability, it's uncertain. There's been a lot of studies on palladium and copper where it actually does migrate in, and so the question is that possible? And so what we thought would be better would be looking at intermetallics. And so there's been a lot of growing research in this direction. Even from the perspective of thermocatalysis, and there's actually a lot of more recent work in the Haber-Bosch area where people are trying to look at intermetallics to improve the Haber-Bosch process. And they really, basically you have a metastable disordered, but then a really, really ordered stable phase if we can get them into the ordered phase. And if this can be a potential improvement in especially stability and durability of your catalyst. And this is essentially how there's many actually ways to create these alloys, but it really does have to do with, basically tuning your synthesis so that you fall within your desired phase diagram. And thermal annealing over time is also one of the best ways to potentially get these highly ordered. But again, it takes time in the lab to figure out the exact synthesis. And so this is what we've been looking at, again, looking at palladium and copper based materials. And then we use basically these, a carbon because it's an electrode, and then some basically stabilizing agents so that we can stabilize it during the synthesis. And this is what they look like when you actually make them. And as you can see, we looked at different size nanoparticles from 5 nanometers to 17 nanometers. These TEM were exciting to us because they really do show that you do have a high degree of ordered copper and palladium in your catalyst. Again, you can see the degree of highly ordered degree of the catalyst here. We could also confirm from XRD that we were getting the highly ordered catalyst that we wanted. And so again, I'm showing you again selectivity data here. Now we looked at both nitrate and nitrite again, and looked at the product selectivity. Here again, looking at nitrogen, ammonia, and nitrite. And essentially, again, for the most part, we either want nitrogen or we want ammonia. We don't want both. And we don't want nitrite because we want all of whatever we put into our system, we want it to react. Again, you can see clear differences. So these materials have the same atomic percent of metals in them. They are both alloys, but very different product selectivity, whether you have a disordered catalyst or you have an ordered catalyst. Most notably here, we're producing with the ordered catalyst, we're getting nearly all nitrogen production. And then here with the disordered catalyst, we're actually getting just a wide variety of products, but a mixture of ammonia and nitrate. Again, we look at long-term stability, and again, the ordered catalyst seems to be very stable. This specific disordered alloy, it seemed to show really different products. And this actually could mean that this is basically thermodynamically trying to move again to this stable form. And so we can see we're actually starting to get more nitrogen and less ammonia with time. And so it seems like we're actually this one is trying to move towards this catalyst. And that's okay, but if you're trying to make a product you want from the start to get the same product, and so the ordered is ideal. The only downside to this was that the order selected towards nitrogen and not ammonia. We also did basically ex situ ZAFs. So this was work that we did at Brookhaven National Lab. This was actually in operando, where we created an electrode with these nanocrystals, and we could, with our electrolyte, and we can look at basically how the oxidation state of palladium and copper changed within the catalyst during the reaction, because again, we want materials that adsorb these reactants. But it's interesting to understand how the electronic structure of these materials changed during catalysis. We actually looked at the palladium and the copper, and there was, I guess this is actually the ex situ data. We also have in situ. I don't think I have it in this data, but essentially there was no significant changes in the oxidation state, whether you had ordering or lack of ordering, but that the higher annealing temperatures resulted in higher coordination of palladium and copper. Again, this can give us insights on how to design catalysts if we can discern what the critical electronic properties are. And with that, this is basically the end of my talk for today. So I'm happy to answer questions, but this has been an interesting direction to start looking at how you can react nitrate to produce ammonia, or react nitrate to basically remediate it for an environmental contaminant. Today, I focus mainly on our basic science aspects, but I'm happy. We also do work on some other aspects on how things like this can scale and whether they can scale and what the challenges are. So happy to answer questions.
Questions? If not, there are. Oh, in the back.
Sorry. I have a question regarding the crystal orientation. How do you control that specific orientation during their growth? And then what's the size range normally do you have? If you go large, that maybe become the random orientation.
Yes, that's a great point. We are going on the order of their nanocrystals, so they're often 10 nanometers in size here, 10, 20 nanometers max. But then how do you grow them? Well, I mean, so there's a lot of thermodynamics associated with how these will grow. And so, and then also, so that's basically one thing, trying to look at diffusion versus deposition of atoms. And so you tune the synthesis to tune the deposition versus the diffusion of the atoms. But then to guide that, you also we introduce basically other things like surfactants and ligands that will thermodynamically adsorb to like one surface. So and then that blocks that surface from growing. And then because it can't block that surface to grow, it has to grow in the other direction. And so it's also tuning those surfactants and the binding to the surfaces. So that's how we grow them. An interesting thing then becomes like actually the more challenging part than even growing the nanocrystals was in taking those extra surfactants and ligands off, because they end up sometimes binding to the surface. And so there's actually a lot of steps in actually taking them off, and a lot of exchange processes in the synthesis. And so that, interestingly, was the harder part than these crystals. And I definitely point to these two papers. Yeah.
Let me just ask, there was a question from one of our viewers online. Has there been any commercial production of engineered catalysts that are currently in the market for any chemical reaction, something that would allow the creation of those faceted catalysts?
That's a great question, and I don't think so. And I think, mostly, the other thing about these is that, one, it's hard to synthesize, and then it's hard for them to even stay stable during hundreds of hours. And so I don't think that we would ever go to a catalyst that looks like this, but I think that this helps us in, if we can identify this helps us identify what facets are active, and then move towards potentially trying to synthesize catalysts that look like this, but then have the exposed facets. And so, but that's my opinion. Some other people probably would like to move faceted research to the scalable way. Yeah.
Thanks for your talk. I had a question that was, I guess, more broad, but I guess you didn't touch on the photoelectrochemistry stuff at all. But can you talk broadly about some of the advantages to doing this in a photoelectrochemical system, and I guess also the challenges of that in terms of scalability and also kind of the fundamental mechanisms of these reactions, specifically for like ammonia?
Yeah, so photocatalysis is like, the interesting thing about photocatalysis is that you have electrons and holes there at the same surface. That's a good thing and a bad thing, because often there's recombination, and so then often you have no charge carriers, but you have the opportunity of having 2 charge carriers as well. And so that allows you to do maybe some unique chemistry that requires 2 charge carriers in a local environment to create some sort of reactant. And that's actually what we've, I didn't present it, but that's kind of what we've been doing, which is essentially we've been looking at how can you use photocatalysis to mirror kind of biological catalysis. And so biological enzymes fix nitrogen at ambient temperature and ambient pressure. And so if you could come up with a catalyst that could mirror the enzyme, you would win a Nobel Prize, probably. But how the enzyme fixes nitrogen is a really unique thing in that it has hydrides. It creates these hydrides which prevent, that are in a certain direction, that they prevent hydrogen production, and they allow, but also decrease the adsorption energy for nitrogen. So and then they also have lots of different protons and electrons taking place in many different reactions in the enzyme. And so what we've actually been doing is actually looking at an alternative reaction pathway where you use those holes to oxidize a carbon species, and you can create a high energy radical. And then that high energy radical can actually allow for the adsorption of nitrogen and the activation of nitrogen. And so this is actually something that you could not do. Like, this is what we're doing in photochemistry. You cannot do that on an electrocatalyst. You cannot do that on a thermocatalyst. And so to me, I think that that's the most unique aspect of photocatalyst. But there's also many, many challenges too. So.
Anything else? All right, if not, let's thank our speaker one more time.